Hey everyone, I hope you all are safe and doing good. So in this lecture we will see one of the most important topic in DSA, that is complexity analysis, mainly time complexity and space complexity. This is one of the most important topic from the interview point of purpose as well. Okay. Although the name suggests complexity analysis, but it's not that much tough. It's easy one. So we'll see what is complexity analysis, basically what is time complexity and what is space complexity. Okay. So this is very important lecture. Now see, I have told you why we need first of all this analysis. So I've told you there are so many algorithms. There can be many ways to solve a problem. That is for sure. Because see, if you now go from one location to another location, so there are many ways. You can go by air, by bus, by train, by bicycle, by uh, your own vehicle. There are so many ways. So is which way you will opt? Which is efficient for you? You decide. You analyze something and based on that you decide. So same, we are having many approaches, many algorithms to solve a particular problem. So then you have to analyze those things and you have to decide which algorithm is good. So that's basically we are analyzing the algorithm, analysis of algorithm, right? Now, what is this analysis of algorithm? Based on some factors, we analyze that algorithm that this is good or not, right? So basically, it is the process of determining the amount of sources like time required, space required to for that algorithm. Based on that, we decide, okay, whether this algorithm is good or not to solve a particular problem. And there are so many algorithms. So the which one is good that we choose. Okay. Now see, if you want to go from one location to another location, so based on many factor like there are so many factors, time factor, money factor. Like you can go by plane, but if you don't have like that much money, so maybe you go by train. Second thing is, if you don't have time, like by train, it take 2 days to reach to that location, and by plane it take only like maybe 2 hours. So if you don't have time, much time, you go by plane. If you have time, you don't have money, you go by train. If you prefer your own vehicle, there is one more way, like you can go by road, your own vehicle. If you have your own vehicle, you can go by that thing also. If you can go by public transport, by buses and all, if you don't go by train. So there are so many factors. You have time, money, and as well as the trade off between time and money. Which one is more important for you? Like for me, I cannot take off for like 4 or 5 days, extra 4 or 5 days. So I prefer by going by plane. I don't prefer by train. That is one thing. So there are so many factors while analyzing the algorithm. Like we have time, we have space, how much time required, space or the memory. Space means memory required to execute that algorithm. During the execution of the program, the memory required, taken by that program, the space taken by that program or that algorithm. Okay. Correctness is also there. If that algorithm or that approach will give correct output every time for every input, there is a trade off between time and space also. Suppose your approach is taking less time, time complexity is less, but space or the memory required is large. And second approach is taking little bit more time complexity, but space required is less. So there is a trade off between these two. You have to choose better one. Okay. According to that, you have to balance out things. Next, maybe you have to analyze best case, worst case, and average case complexity analysis. What is these things? I'll show you that thing also. I'll tell you that thing. Best, worst, and average case. So there are so many factors while you are analyzing the algorithm. And based on after analyzing, you will get the suitable algorithm or suitable approach to solve that particular problem. Yes. Now, what is complexity analysis? So out of all these factors, this time complexity and space complexity, these two factors, these basically comes under complexity analysis, mainly these two factors. So complexity analysis focus on time complexity and space complexity. So we can say Like complexity analysis or complexity analysis is a subset, or you can say that it helps us to analyze an algorithm, or it's a subset of analysis of algorithm, because analysis of algorithm contains many factors: time, space, correctness, trade-off between time and space, best, worst, average case analysis, these things. So complexity analysis is, it's like a subset of analysis of algorithm. It focus mainly on time complexity and space complexity. So in this lecture we'll see, and these are important. Mainly time complexity is important. Space complexity is not that much important. Okay. Time complexity is crucial. So we'll see in this thing time complexity in this lecture. So why do we need this? It's crucial for selecting the most efficient algorithm for a specific task, optimizing code performance and predicting the resource uses, how many memory would be required and something like that, the resource uses, and ensuring the scalability. Here, one thing, the scalability is very important. Okay, this thing is very important here, because in software development, when you are developing a software or an application, two things are important. One is readability. So that should be like, readability means your code should be readable. I mean, if I want to read that code, I want to understand, or any other developers who these understand the code, it should be like readable, clean. Second is scalable. Scalability. Scalability means your code or your program or your software should be scalable. Scalable means it works on the large amount of data as well. Like if I have written an algorithm, something, or a program or algorithm or an approach, it works on a 10 integer, or the data is like, the size of my data is 10. So that if suppose size increase, my data or my problem size increase, it becomes 1000. So that approach should work on 1000 elements as well. If suppose 10,000, so that approach, that algorithm should work on 10,000 element as well. So it should be scalable. Like if suppose there is my website Jenny's lectures. So when we were like working on that website, so it's not like that we were in our mind that we have that thing that, or okay, only 50 or 100 user will use it at a time, so we can make a simple website. No, we are having that if suppose at one time I become so much famous that many users are accessing that website, or almost like 1 million user, 1 million students. So at that time it shouldn't crash, it shouldn't hang, like it should work properly. So the your software or your application should be scalable, it should work on the larger, if the problem size increase, then also it should work, that kind of thing. So while developing software, obviously we focus on that thing. So same, while selecting an algorithm also, that should work, like that should ensure the scalability also in that particular software or application. Okay, it should work on larger amount of data as well, right? So it helps developers make like some decisions about algorithm design and implementation. Now complexity analysis, I have told you, this is like basically focus on time complexity and space complexity, right? So it ensures that we select the best approach to solve a problem, especially while dealing with large amount of data. Why large amount of data? I have told you, because scalability is important in software development. It's not like that if your algorithm is working on small amount of data, it will also be efficient or on large amount of data as well. No, it's not sometimes true. There are so many algorithms, we'll compare those also and we'll see that thing. So main purpose is scalability, that should work on larger amount of data as well. As your data grows or input size grows, it should work properly, right? Okay, so that is complexity analysis. And why we need it? Obviously it helps us to compare the algorithms and choose the most efficient solution for a given problem, right? Some real life example, like if you are searching a name in a phone book, then linear search, binary search, you don't know about linear search or binary search right now, but linear search is something like, if you have an array, because we will be using these two examples, so let me just clear this thing first. What is linear search? So suppose we have an array. Here we have 10, 1, -1, 0, 20. So the n is 5. N means the number of elements, the size of this. Linear search means suppose you want to search an element, 0 is there or not. Linear search. So we start from 1, we compare. Is this 0? No. The next element. Is this 0? No. Then next, then next. Is this 0? Yes. So linearly you are searching. If you are searching for like 30, then again compare with the first. Is this 30? No. 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 So this is linear search. So the worst case is if the number is not present, like 30 is not present. So how many comparisons you have done with this, with this, with this, with this, with this? Like 5 comparison we have done. Okay. If suppose there are 10 elements, then we will compare 10 times. We will compare with all the elements. Will we find that thing? Okay. So the number of comparison are like equal to whatever the size of element, whatever the input size, size of that array. Got it? This is linear search. One by one we are searching. Now binary search is what? For binary search, it works on sorted array. So just first sort this array. Okay. While sorting, at first we are having -1, 0, 1, 10, 20. And now we are searching for suppose 30. Or at first we were searching 0. So binary search works how? Let me just briefly discuss here. We'll see what is linear search, binary search, because these are searching algorithm in detailed manner. Don't worry. This is just a brief introduction for just this lecture. Now in binary search, we first n is 5, so we divide it. 5 by 2 means it would be like 2.5. So let's consider 2 only. So 0, 1, 2. So this is like half. So we divide this array in half. Now compare with this. Is this 0? No, this is 1. Now one thing is for sure in binary search, whatever the elements on the left hand side of this element is always less than this element, and whatever the element on the right hand side is always greater than 1, because the array is sorted. Yes. Now we are searching 0. 0 is less than 1. Yes. So you don't need to search in this half of the array. We will search in this half. So you don't have to search the entire array. Half we will search. Again, now in this array we will search. Right? So again, now it's 2. N is now 2. So again divide by 2. So 2 by 2, that is 1. So at 0, at 1 is this location. Go for this location. This is half of this array. Now compare. Is this 0? Yes, this is 0, and that's it. You will get it. If suppose you are searching here -2. So this is not -2. Okay. So one comparison is this. One comparison was this. Two comparison we have done. Now is -2 less than 0? Yes. So we can get here on the left hand side of 0. And 1 divided by 2. Obviously it's 1 only. So we'll not further divide it. So we have here only like we can say one element. So definitely we compare -2 with -1. It's not -2. So the element is not present here. So we have done here only two comparison. One is this, one is this. And here you have to compare with every element. Yes. So here almost 1, 2, 3, 4, 5 comparison. And here we have done only 2 or maximum 3 comparison with this also. So 3 comparison. That's it. So number of comparison are less. Number of operation you have performed are less here rather than linear search. So this is linear search, this is binary search. Okay. Which one is better? Obviously, if the data is small, if there are only 5 elements or 10 elements, it doesn't matter. You can go for linear search, for binary search. Linear search in that case is better because it will not take like much time if the data is only 10 or 20 elements. But if the data is 1000, n is 1000 in this case. N is suppose 1000. So you have to compare 1000 with 1000 elements. In the worst case, Suppose the data is present in the last of the array, at the last. So thousands or the 999 element is whatever the element you are searching. So you have to compare with every element, right? So there are 1,000 comparisons, 1,000 operations. It's really tough. Definitely. Now data is 1 million. If your problem size increase, you are working on a large project. If data, obviously the data set is 1 million, 2 million, 5, 10 million, then obviously those many comparisons are of no use and it will take a lot of time. So that's not a good idea. Now binary search in that case is good because it is dividing the array by 2. So if the data is 1,000, so we'll not do 1,000 comparison, which divided by 2, so 500, like in the middle. So either the data is in the right side or the left side. So one comparison, if in the left side, again divide by 2. This is, again we are compare with this, so 2 comparison. So it's like 250, like almost half is 250. Again if the data is on the, suppose, left hand side of 250, so again divide by 2. So there are very less comparison rather than linear search. So almost in this case we will having almost 10. Within 10 comparison, within 10 operation, you are going to get your output, whether that element is present or not. So 1,000 comparison is good or only 10 comparison is good? Which one is good? When the data is large, obviously binary search, obviously this approach is good. That's why I'm saying we generally take larger amount of data. We analyze those algorithm based on larger amount of data, based on scalability. Because for smaller amount, it generally, like, it doesn't matter which algorithm you can choose for 5 element or 10 element. It doesn't matter. Okay. Now I hope you get a little bit idea about linear search and binary search. Okay. So now which one is good? Now in this case, suppose you have a dictionary. So if you want to search a alphabet, suppose I want to search what is the meaning of this bother. Sorry, where is bother? What is the meaning of this? This. So it's not like that I'll start from the searching, from the starting only, from the first word, then second, third, fourth. No, I will directly go. We have indexing with B, then BOTHER, and directly will go that thing because everything is sorted in alphabetical order. So we can apply binary search here. Okay. Okay. We are not applying like binary search specifically. We are applying like maybe you can say indexing kind of thing. We directly search for B. Okay. But this is better. Binary search is definitely better than linear search. So it basically, you can say, provides a framework for evaluating the performance of algorithms. And if you understand the complexity of the algorithm, the developers or we can make proper decisions about which algorithm is used in different situations, where to use which algorithm. That's why we always say that interviewer always asks you the optimized approach, not the brute force approach. Okay. Now, first, what is now time complexity? Now the main topic comes. What is time complexity? See, one thing I want to tell you here is, first, time complexity is not equal to the time taken by the program while executing the execution time. We measure that time in some milliseconds or seconds. Like in the previous case, also in few examples when we were discussing file handling, if you use buffered reader, then it take less time. And if we don't use buffering kind of thing, then it take more time. So that time we measure generally in like milliseconds or seconds. So do you think that is time complexity? No, that is not time complexity actually. First thing you have to clear this thing. Suppose there is two, I have written a code. Suppose I have written a code for linear search. You know now what is linear search? Let's just try to write down a code for linear search. There is an array. So x is 30 and I want to search this x is present here or not. Linear search basically. So how to search? The procedure you know. We start from here, then compare with this till we find that element. So the loop would be from starting to end. So we'll take I is equal to 0. We'll start with int. It's int. I should be less than whatever the array dot length. Name is arr, so array dot length and I plus plus. I'm not writing the exact code. It will not work. Okay. I'm just writing the logic, just the for loop. That's it. And I plus plus. Okay. Before that, we are having an array, like we have an array int, name is arr and new int. And here we have like 10, 1, 5, 0, and 20, this kind of thing. So this is what array. Now here we check if this x equal to arr and I, then we simply print here x is found, something like this. Simple, right? So this kind of loop is there. Although whenever the x is found, you can break it also. It's not that much efficient code. You can write down here break. As soon as you find x, break the loop. You don't have to search next. So this is simple code for linear search. Now suppose on my machine, I'm having only 5 element or 10 element or 50 elements in the array, and it is taking suppose almost 200 milliseconds. If suppose the data is 50, n is 50. Here in this case n is 5, but suppose n is 50, so it is taking 200 milliseconds, right? Now the same program, the same algorithm, the same for loop on a second machine, my friend is working on my friend's machine is taking only suppose 100 millisecond or 150 millisecond, something like this. So can you say my code is good, or can my friend say that his or her code is good? Or you can say, or can you tell me which is having less time complexity? If suppose my machine it is taking 200 millisecond, on my friend machine is it is taking suppose 150 millisecond. So which is having less time complexity? We can't say, because time complexity we cannot measure in milliseconds and all. It is the actual execution time taken. Maybe my machine is the old machine, it is having only i3 processor. My friend's machine is having i9 processor. So obviously it depends on the power, the CPU, right? The resources or the type of laptop my friends have. If that laptop is good than my laptop, then obviously it will run faster than me. And obviously the program is same, the data is same, the size of the data is same, but still it is taking less time. So it depends on the hardware of CPU. I mean the hardware of, you can say, your machine. There's so many resources, which processor you have in background, how many processors are running and all, how many software you have in your laptop, the load on your machine, basically on that hardware. It depends on many factors. It is not time complexity. Time complexity is same. Time complexity of this algorithm or the approach you are following is same, because everything is same. The for loop is same, the data is same, and everything is same. So time complexity is same. So what is basically time complexity? Time taken by the execution of your program is, it's not the time complexity. It is measured in milliseconds or seconds. It depends on many factors. The hardware you have, the CPU you have, right? But that is not time complexity. Now, what is time complexity is? Let me tell you. So, time complexity is basically, it is the measure of the amount of time taken to run an algorithm, to run an algorithm as a function of input size. Input size is, we generally take n. This line is important. As a function of input size. It's not exactly the time taken to run that algorithm or to run that program. No. Obviously, it's a measure of the time taken or the amount of time an algorithm takes to run as a function of input size. So basically, it depends on the n. So it will show, you can say, the relationship. How the time grows as the input size grows, as the input size increase. So it shows that relationship, right? Now, what does that mean? See, if I have to calculate time complexity, if I say of this algorithm, of this approach I'm writing here, so basically you just uh, compare, or you just find out the number of operations or the number of comparisons you have done in that program to find out the time complexity, right? Like if you're writing this thing, so it will take like order of one. Why I'm saying like order of one? So generally there is a notation big O. We call it big O. So big O notation. The worst case time complexity we measure in big O. And why worst case? I'll tell you, I'll explain that thing in a few minutes. But when we are having the time complexity, you generally everywhere you will say that big O notation. There are many notation also like theta we have, omega we have. This thing we'll discuss later. But the most commonly used is big O because that show the worst case time complexity. Okay. And you can say that it's order of here we can say here if you want to calculate the time complexity of this, then you have to calculate the number of comparison. Okay. Now in this case, if n is 50, let me you tell me if n is suppose 5, number of comparisons are 5. In worst case, I'm saying in worst case means the element you want to find is, I mean, the last element, suppose 20. So the last element 20. So you have to compare with all the elements. If n becomes 50, and in the worst case, number of comparison required is 50. You have to compare with each element, whether this element exists or not. Number of elements become, n becomes 1000. So number of comparison becomes 1000. Yes or no? So these number of comparisons depends on the size, input size. So how basically how the increasing, how this number of comparisons or the time complexity is increasing linearly with the input size, right? It's directly proportional to that input size, right? In this case. So if you draw a graph in this case, so we can say that here time complexity is order of n. Order of n. Based on the procedure you do, you can calculate time complexity. Or based on the code you have, you can calculate time complexity. To simply run these kind of statement, simple statement, it takes constant time, like order of 1 only. So generally we ignore this. We just focus on the frequently executed statements. And what are frequently executed statement here? Only these statements. Why frequently executed? Because these are in loops. So focus on loops, recursion, function call to calculate time complexity. These constant time complexity doesn't matter, doesn't make any sense when you are dealing with a larger amount of data. I'll show you that thing also. So you have to calculate time complexity of the frequently executed statements or on the loops. So find out time complexity of this. Basically, it's nothing but you have to calculate how many operations or how many comparisons have been done here. Operation here is just we are comparing. We are comparing. How many comparisons are there? Till whatever the array length, starting from 0 till array length. So 0 to n. These many comparisons are there. So time complexity is, and we consider worst case. So it is order of n. Worst case means the element is at the last, or maybe element is not present. That is also worst case. So it's order of n. Maybe sometimes you say that, ma'am, suppose I want to, the x here is 10. X here is 10. So in that case, we just compare with first one. You get the element and that's it. We simply suppose here write break. So you break. There is only one comparison. So in that case, it's order of 1. Why you are saying order of n? This is the best case. Every time, suppose you have 1 million data, 10 million data, every time whatever you want to search is present at the first element. So you don't need to search further. At the first element only compare with this and you get the output. Yes, element found. So this is the best case, but obviously best case doesn't exist every time. While choosing the type of algorithm, we generally take the worst case. What can be the worst situation? In general life also we consider like worst situation. It's not like that every time we'll get best thing. Like one example is now Mahakumbh is going on in Prayagraj. So we went there. Now at that time I mean, it was very, well, we were having a smooth experience. We were going through our own vehicle, and we were not stopped by anyone. And till Sangam, we were there by our own vehicle, and that's it. We just have to walk only like 1 or 2 kilometers. That's it. So it was very smooth for us. That is the best case. But based on that, I cannot say that you go by your own car, because sometimes you have news that there is so much like traffic jam, and you have to walk 15 or 20 kilometers or 30 kilometers in Prayagraj. They don't, allow the, you can say, the vehicles from other states and all. It's a no vehicle zone, that kind of thing. So when we went there, that was like, it was best case, because there was no rush at that time. But sometimes there is rush, so you have to consider worst case as well. You have to see that situation now. Right now, what is the situation there? Maybe you have to walk 15 kilometer, 20 kilometer. No. So your vehicles are not allowed there in that case if there is rush. Okay, so think about in every situation in real life also, we generally think about the worst situation. What can be the worst in this case? It cannot be worse. It cannot be more than this thing. So here the worst case is the time taken, or the time complexity cannot be more than order of n. That is for sure. It can be less than, maybe that you will find that thing here in the middle. Suppose x is 5. So you will compare 1, 2, 3 comparison, you will get here. You don't have to compare till n. Maybe at first only you get. So order of 1 you need only. So this is best case. If here you get, this is like average case. Not best, not worst, but average. If you get here, it is the worst case. So generally we consider the worst case, right? So like while going to, like if you are going to planning to Mahakum, you have to consider the worst situation as well. Maybe you got stuck in the traffic jam for, I have got the news like the people are stuck there for almost 2 days, 24 hours, 48 hours. So that can be the worst situation. If you can handle that situation, you go by your own vehicle. You just take that risk. Otherwise, you buy some expensive flight ticket and go there by flight. Okay. So generally we consider, why we consider worst case. I think this thing is like little bit clear to you. Same example, like one more example we can take here. Same example, like if we are working, or we are designing a website. So if suppose 10 users are accessing that website at one time, okay, and maybe 1 million user are accessing that website. So the chances of getting crashed the website is in which case? In 1 million user, if you are accessing, then in that case, the chances are more that it get crashed. So you have to handle that situation. We cannot think that, okay, 10 or 50 user will access that, and so just make a simple, very basic website. No, there can be a worst case. Maybe 1 million user or 2 million user will access someday your website. So you have to make your website, that you have to handle that situation. You have to handle the worst case as well, right? So that's why, while calculating the complexity also, first rule is, or first point is, like consider always worst case. And worst case, or is expressed basically in big O notation. Big O notation. This is big O notation. So that's why everywhere you see this big O notation, this capital O, big O notation. Here we write down the function of like n, we can say, in terms of n. So time complexity is expressed in big O notation. Time taken is expressed in second or milliseconds, right? That's why everywhere you think about big O, big O, big O, big O notation. Okay, generally we consider worst case while considering time complexity, while calculating time complexity of any algorithm or an approach. Okay, now for this we know it would be order of n, because it's linear. So this is how, I guess, it's not that much tough. If you are given a algorithm or given a particular code snippet, you can easily find out time complexity. You have to just focus on the identify the number of operations are going to perform there. These are basically going to take this assignment. These things are taking only order of 1 constant time. So you have to more focus on the frequently executed statements, the loops, recursive calls or function calls, these things in your program. Here we have only one, like this for loop. So focus on that. How many comparisons are there? The operation is comparison. How many times this line has been executed? How many times the loop is executed? Basically, just go for how many times the loop is executed. That's it. So we have, you have found your first time complexity. That's very simple. Order of n. This is how we find out time complexity if any code is given. We will see practically many example in the next video how to find out. I'll give you the code and you have to find out time complexity. Don't worry. But here you have to understand what is time complexity. So it's like if I draw the graph of this, suppose this is linearly. This is linear time complexity. So if I draw the graph of this thing, see, suppose, so it's like the graph is between number of elements you have and the number of operations to be performed, operation number of comparison we can say. So it's basically give you the time complexity, give you the relationship between these two. How these number of operations grows with the input size. Okay. Now what would be the graph here? See, if the number of elements are 10, then we know it's equal to n only. So n is here 10. So 10 comparison would be there. So now here, obviously, this would be 10 number of comparison, number of operations we can say. If it's 20, n is 20 number of element. So same here we have 20 also. So here we have till 50 suppose. If it's 20, this would also be 20, something like this. If n is 30, number of operations are also 30. If n is 40, number of operations are also 40 here. If it's 50, then these are also 50. It's here. So if you draw a line something like this, then this would be something like this. So it's a linear time. Order of 1, or you can say linear time. It's order of n. You can draw a graph something like this. This is linear time complexity. It is taking linear time. This algorithm is taking linear time. Right? But now again, if n is 1000, so there are 1000 comparison, it is going to increase. If n is 1 million, so 1 million comparison. It's not a good approach. For small data, it's fine. It doesn't matter really. But we focus on the larger data. For that, binary search is better. Let me just, in binary search, if we are going something like this, in binary search, if the array is sorted, so let me just write down one more state that you can say code for binary search. If you're not getting the code, don't worry, I'll just write down the simple logic. We'll see binary search code or binary search algorithm in detail. Don't worry. So how this will go? I is n, whatever the n is here 5. Number of elements are 5. So n is equal to 5 we can say. I is 5 and I should be greater than equal to 1. Right? Or it's only greater than 1. So I would be I divide by 2. We divide it. And whatever the code of searching we'll write here. Those statements. So something like this we write. Although it's not the exact code, but I just want to tell you the essence of this thing. So every time we are just dividing it by 2. Or mainly in this case we use like while loop kind of thing. So we are not going from here to here. We are dividing the array by 2. Then again dividing by 2. Then again dividing by 2. So if this kind of pattern is there in the program, then it is log n. The time complexity is log n. You have to take care of you have to like memorize some points. So it's log n. If you go for log values, then you have the idea about this thing. Okay, and whenever you are going, when we'll discuss binary search in detail, then I'll tell you why log n and all. But if you are going like divide by half, something like this, successively dividing by half, then it's log n. So time complexity here is order of log n. Right? And log n is something like this. If I write down the, you can say the values. If n is log n, base is 2. Base is 2. So n is 10, 20, 30, 40, 50. For that, it will not go linearly. It will go logarithmic, like log n you have to find out log 10, log 20, log 30, log 50. Let me just write down the values for that here. So these are some like log values for 10, 20, 30 and all. If you draw a graph, this is binary search and it is taking log n. I've told you if this kind of pattern is there, successively dividing by 2 the input size, then it takes the time complexity would be for that approach is log n. There for that you can say this for loop is log n, right? Now these are the things. If I draw the graph here, same. Here we have elements, the size, and here we have the number of operations, right? So in the previous case, it was linear. In this case, it's 20, 10, 20, 30, 40, 50, and up to suppose 100. So this would be something like this. If I have here, it's not that much like linear. See, log 10 is 3.3. So if I take here something like this, suppose here we have 10, 20. So it's like 3, 3.3. It's like 4.3, something like this. 30 is like 4.9, something like this. 5.3, 5.3, 5.6, 5.9, and 6.1, 6.3. It's like less than 10, right? And 6.4 and 6.6. So linear graph would be something, sorry, this log n graph would be something like this. It's not increasing new you directly, something like this. Not, it's not like linear kind of thing. It's like, so if you have log n, so this is more scalable. It will move something like this steadily. It will not go directly high, something like this. That's it. So although in the starting the difference is not that much, maybe for something, for some input where you will get this graph. Right now it is this, but for some input maybe you have the graph something like this. This is log n and this is order of n. So maybe in starting for this data, this linear is having less time and this is having more time. Maybe a case. But we don't consider smaller data. We consider larger data. Once you go here, suppose the log n is this and you have fixed the input size here 90. So see the difference. This is taking more time. This is having the number of operations are less here more. And this gap will increase if the size increase. So this would be steadily. See something like this only. So this gap would be increasing. So which one is better when larger data you consider? Obviously log n is better because there we have less number of comparison. In starting it doesn't matter. For small data it doesn't actually matter. For 10, 20, the size is 10, 20, 30, it doesn't matter actually. That's why we consider larger amount of data while calculating time complexity. Okay. Okay, this is what log n graph, something like this, and this is order of n graph. I hope you got a little bit, right? So if the size, if here the n is 10, sorry, n is 100. So if the array is sorted, you just sort the array, apply binary search, and you have to compare only at most 7 comparison you need to, I mean, there would be only 7 comparison, then you get the result. But in linear time, there would be, in worst case, 100 comparison. But in this case, in worst case, only 7 comparison you need because you are going to divide that size by half. Okay. I hope you got this thing. Now, what is time complexity? I hope you got this thing now. It's basically giving you the relationship. How the time grows as the input grows. How? It's not, it will not give you the exact time in milliseconds or seconds. It will just give you the relationship. That's why I'm telling you that it is like as a function of input size. It is like measure of the amount of you can say the time an algorithm takes to run as a measure of, sorry, as a function of input size. As a function of input size, it depends on the n. That's why it's a function of n. It's a function of n, not exact time, right? So mathematically we express this as order of or big O of n or log n, whatever complexity we have. So we can say that this time is a function of n. It's a function of n. It's not exact the time taken. Okay. So I hope now you got the idea what is time complexity. So it measures the growth rate of an algorithm's execution time as the input size increase. It measures the growth rate. How the time is growing as the input grows. So that's why, and from that graph, we can easily say algorithm which is having time complexity log n is better than an algorithm which is taking time complexity order of n, because the as the graph says, if it takes order of n, then it will move something like this, and if it's log n, then it will move something like this steadily. So see, the number of operations are less here when the number of size increase. Here it would be more. So we can easily say that this order of log n is better than which is having order of n. This one is better. So that's why we compare. If an approach is taking this time, so that would be more better approach than this approach. So based on this, we compare our algorithms. How much scalable your algorithm is, your software is. It depends on based on the algorithm you have used there, the technique you have used in that application or in that software. Okay. So that's why these time complexity things matters. In interview also they expect from you that you give a better approach. Better approach means the time complexity would be less. Okay. So this is less, this is greater. And sometimes there is constant time complexity. I'll tell you that thing also. I'll show you that thing also. Don't worry. That is obviously better than everything. It's constant. Okay. Now, see, it is not the actual time. This thing I have told you. It is different from the actual time taken. Okay. Because the actual time taken depends on the hardware, software, and some other factors as well. Okay. So, focus on scaling. Scalability is important. So, time complexity focus on how the algorithm's runtime scales with the input size rather than precise execution time. How is the growth? Okay. So it is basically the theoretical measure. It's not practically in seconds or milliseconds. It's theoretical measure that allows us to compare like the efficiency of different algorithms. Okay. Now, next is bigger notations. I have already told you. Generally, the worst case. This is the worst case complexity, and why we consider worst case that also I have told you. So we, n- you can say write down that thing in a bigger notation. So it describes the worst case, or you can say the upper bound of algorithm's time complexity. It represents the worst case scenario. Means in linear time, it's order of n. So that algorithm, that linear time searching algorithm will not take more than order of n. The time complexity would be maximum order of n. Maximum number of comparison would be the number of elements. That's it. We know. So that is the upper bound. That is the worst case. It's not more than that. Maybe you get the solution or you get the answer less than with order of n, less than n with n comparison. Maybe only one comparison is sufficient, or you get only n by 2 comparison, but it doesn't matter. We take the worst case. And why worst case? Because it provides a guarantee on the algorithm's performance, ensuring it won't take longer than expected. It won't take longer than order of n. So it gives you that guarantee. That's why we consider like worst case. Okay. So if you know in advance the worst situation, you can plan accordingly. Like if you are going to Mahakum and you know the worst situation, then you can stuck there for 2 days all. 2 days or 3 days in the traffic. That is the worst case, not more than that. So you plan accordingly. Maybe if there is no other choice and you have to go by your road and by your own car, then accordingly you plan. Maybe you have extra food or something like this, your power bank and all. So you prepare according to that situation. So that's why it allows us to plan the resources and ensure the algorithm meets performance requirements. So accordingly we'll plan. Okay. So BIGO serves as a critical tool for accessing the performance limitations. So BIGO is very important. That's why everywhere, in most of the cases, we know BIGO. And in interviews also, they mainly focus on the BIGO notation. So you have to compare your algorithm based on this BIGO notation or this worst time complexity, worst case complexity. Right? Now, what are some rules for calculating now time complexity? What things you need to take care to need to remember while you are calculating time complexity of an algorithm? First, always consider worst case. Why worst case? We have already discussed. Okay. Okay. Next, one thing is constant time operation. So, basic operations, arithmetic, assignment, comparison, these take constant time. Constant time is order of n. Okay. Like int x is equal to, in the previous case, is equal to 10. So, that is constant time. It will take assignment, will take constant time. So, order of n only. Sequential statements. Time complexity of a sequence of statement is the sum of the complexity of individual statements. Like if you combine, if statement 1 is taking order of 1, statement 2 is taking order of n, so we combine both and the complexity would be order of like something like this. If we have this kind of thing. See, in this case, this loop is having complexity order of n, and these statements, suppose we have one this, so these are having like plus 1, we can add 1, order of 1, order of 1, something like this. So n plus 2. So we, rather than writing this, we simply write order of n only. One rule is while calculating time complexity is ignore the constant. These actually doesn't matter, because if n becomes 1 million, so does this 2 matter here? N is 1 million and plus 2. It doesn't really matter. And we know that while considering time complexity kind of thing, we consider larger amount of data. We calculate time complexity for large amount of data. So ignore the constant. Just take order of n. This is one of the rule of calculating time complexity. Ignore the constant. Okay. And if there are suppose two loops, one loop is this, one again we are having the same loop. So this loop is taking comparisons are order of n. So like order of n. One more loop we are having, that is also running from 1 to n or 0 to n. So that is also having n. So it would be n plus n. They are exactly same loop, suppose in the program. So it becomes order of 2n. So we ignore the constant and that would be simply order of n. So in bigger notation, we simply write this thing, not 2n. Because if n is larger, it doesn't really matter. So we ignore the constant. So it's order of n only. Right? Because see, in this case, if this is 2n, it's order of 2n. So how we can do that thing? How we can draw this? If it's order of 2n, n plus n. So it's 2n. So if n is 10, it would be 20. If n is 10, so it's 2n. Number of operations are complexity is order of 2n, na? N plus n. So that would be 20. If it's 20, then it would be 30. If 30, then 60. If 40, then 80. If 50, then 100. But the line is something like this only, na? Although the previous line was something like this. But both are linear. Ultimately, the relationship is linear only. This is a little bit more steep. Okay. So we focus on the relationship only. Constant doesn't matter. So we drop the constant. Ultimately, if the line is something like this also, If it's n by 2, then for 10, it would be 5. For 20, it would be 10. Then for 30, it would be 15. So the line would be a little bit something like this. But ultimately, the relationship is linearly. These are growing. So ultimately, for this, we ignore these constants and we just write down the relationship between this, the number of the time and the input size. That is order of n. That's why it doesn't matter. The constant doesn't matter actually. The relationship matter. So it is order of n only. That's why we drop the constant. Right? Now, one more thing is, let me just show you this thing with a practical example. So let's create a new project, data structure and algorithms, IntelliJ and Java only. And in this, let's create a new package. com.jennyslexus.basics. And in this basics, let's create a new Java class, time complexity. Now here, suppose we are having a function, linear search. So this is our basic like program for linear search. We have a function, we have a method, sorry, linear search. And in this class, we are having this method, definition of this method, and we are calling this in this main. Right? Simple. So if you run this, suppose I run this, but the 5 is not there in this array. So you will not get, I guess, anything. You will not get any output here. See, if you want to find out you can say the execution time taken. So we have one thing here. We can just do, we have system dot nano time. This thing. Let's start this time here, and after getting the output here, after for loop, let's just have elapsed time is equal to whatever the right now system dot nano time minus whatever the start time. That's it. And we can simply print this time. Just divided by 1000, so you get it the time in millisecond, because it will give you time in nanosecond. This thing we have already done many times. So if I run this, almost 1 millisecond it is taking, right? And we are searching here, but that time taken is not time complexity, right? If this array, suppose let's take, we are having an array of size 50, and I'm just going to fill in this arrays dot, we have a method arrays dot fill, and in this array I want to fill everywhere 10. Every element is 10. The size is 50, right? Let's run this. Right now it is taking 4 millisecond. If I increase this 500, the size of the array is 500, there are 500 elements. Let's run this. See, it's 13 millisecond. If 5000 elements, if I run this, it's 130 milliseconds. So as soon as, like, as you increase this, the input size, obviously the time taken is increasing. Is see, right now it's 8311 milliseconds, almost 8 seconds, 8.3 seconds, right? But the time complexity, that is not time complexity. Time complexity is same because the algorithm is same. That is execution time, actually actual time taken. That is not time complexity. So while calculating time complexity, we focus on the number of operations, or we count the number of operations. So basically you have to analyze how many times loops, or if there is any recursive call, recursion we'll discuss later, or function call execute, how many times. So here this is executing, like we have this loop. So mainly this matters. This is executing how many times? Till array dot length. If array length is 10, then 10 times. If 20, then 20 times. So it's order of n. It's simply bus. I've told you it's order of n. We write down this mathematically. It's an order of n. So it's a function of n. It depends on n, right? So this linear search, this method is taking order of n or the linear time. Next point is we always consider, I've told you, worst case complexity, right? Maybe in this case, if there is everywhere we are having 10 and I want to find out 10 only. So at first comparison, you will get 10. So that is the best case. But we consider worst case while calculating uh, for an algorithm time complexity. We are going to drop the constant. Suppose here we write there is this thing, this method, and here. So we are not concerned with this time and all. This is of no use because we are discussing time complexity. So let's just remove all these. And here, let's just add one more for loop. Suppose this is one more loop. So we have this method. In this method, we are having this array. One is this, and one is one more for loop. This from 0 to 100. So this doesn't depend on the n or the size. It is constant 100. So the comparison, how many comparisons are there? For this statements, this statement, how many times this statement would be executed? How many operations are there? 100. So it's like we can just write down it's order of 100. For this loop, order of 100. 100 comparisons are there. For this, order of n. So we can write down for the complete method, we can write down here it's order of capital O, order of n plus 100. Yes or no? If this is the situation. Because there are two for loops and you have to obviously analyze these loops, how many times these statements has been executed. You have to focus on frequently executed statements. But if suppose n is 50, so yeah, in that case 100 matters. If suppose n is 100, so in that case also 100 matters. But we, while considering the time complexity, we consider large amount of data. If suppose n is 1 million, so does this 100 matters in this case? 1 million plus 100? Not really. So that's why we always drop the constant. You can just drop it. So we simply write order of n. Simple. And one more case is there. Let me just show you one more thing. If suppose, let's just comment out this thing. We have this array. We have this array. Let's just comment out this thing also. And I want to find out like the sum of pairs. Like pair is 10 and 7. So it's like something like this. We are having here pairs 10 comma 7. One is this. Second pair is 10 comma minus 4, like this. Like this. We have 10, then 10 and 7, then 10 minus 4, then 10 20 and 10 50. Then we take the 7. Then 7 10, 7 minus 4, 7 20, 7 50, like this. Yes, if you want to ignore this 7 10 because this is duplicate, so you can ignore this also. Okay. Let me just discuss this thing on the board. You will get that thing better. So how to find out pair? I want to find out one more thing. One is like that linear search only that we have already have in that program, and I want to add something more. Linear search as well as I want to find out the pair of sum of pairs. So pairs means we just take this like 10. 10 with 4. Again 10 with 5. 10 with minus 1. 10 with 7. Now we take next element 4. 4 with 10. So you can ignore this because it's already there. So 4 with 5. Then we have 4 with minus 1. Then we have 4 with 7. Then we take this element 5. Then 5 minus 1 and we have 5 7. Next we have minus 1 7. So I guess these many pairs we'll have here. So I want to find out sum of all these pairs. Yes or no? How you will find out? We have one loop here. So it will go from 0 till less than array dot length, we know. Because first we'll find out pair with 10. So we fix this 10, fix this 10, This is suppose I, and we change this. See, 10 is fixed and we change this. First 4, then 5, then -1, then 7, something like this. Then we fix second element 4 and we start from the next element. So 5 -1, 7. This element is changing. For each element, we fix one element and again we are checking with all the remaining elements. Right? For this, we are having, we are comparing with n-1 element because n is 5, so there are n-1 element. N is 5, so there will be 3. So we take only n-2 element. Then we take n-1 element. Then something like this. We take n till 1. Right? So it's I plus plus. For this, obviously, we need two for loop, nested loops. Because I is fixed, so I fix this. Now this is changing. So now we have j. J is equal to whatever I plus 1. I was 10, so I plus 1 is j here. So it's 4. So we'll start from I plus 1 and till end we will go less than same array dot length. I hope you got this logic. It's not that much tough. We have already discussed one problem, how to find out sum of pairs. Now simply we can do like if we have one element and sum at first, a variable. So sum is equal to array of I plus array of j, and we can simply print whatever the sum is. It's not that much tough. But now calculate the time complexity of these four loops. See carefully now. This loop, outer loop is running from 0 till whatever the n length. So it's like obviously n, order of n times it will run. Inner for loop, it is running how many times? Now for this loop, how many times these things are running? We are again having a loop, again for loop. It will start from I plus 1, like from here, and go till the end. Yes. So at first, if suppose you will not take at first, I'll take from 0 only. Again. So this will also go from 0 till end. Yes or no? So this is also going from 0 to end. This is also going from 0 to end. So frequently executed statement. These statements are executing how many times? N square times. N square. Yes. I hope you got this. N into N. It's not 2n. We'll not do plus. It's n square times. These statements would be executed n square times. Right? You can write in this and you can see. So this is having order of n square. Time complexity. N square. If you take here, not this, I'll take I plus 1 because I don't want to take the duplicate set. I want to start 10, then with 4, and if I is here, then I want to start from here. I will not make a set with 10 previous. No. With next one. So with I plus 1. So how many times these statements would be executed? At first I is 0 and this is I plus 1 here. So how many times? 4 times. 4 times, or you can say that n minus 1, because we'll start with I plus 1 here and we'll go till the end. So n minus 1, then n minus 2, like this till 1. Yes. So it's like sum of n natural number. So it would be n into n minus 1 by 2. We know the formula. So it's like you can hear something like this. N square. You definitely get here n square. N square minus n by 2. So like n square by 2 minus n by 2. So we ignore one more rule is of this big O notation, or while calculating the time complexity. One more rule is ignore the less dominating term. N square by 2 constant we ignore. N square minus n. So it's like if n is suppose 10, so n square is 100 minus 10. To somewhat maybe it matters. Suppose n is 500. So n square is this one minus 500. Is really 500 matter here? Or if suppose n is 1000, or 10,000. So here we have 10,000 square minus 10,000. So this n doesn't really matter when the input size increases. So the more degree n square, this is having more degree. So this is n is less dominating term. So we just ignore this. So simply we can write down order of n square. So ignore the less dominating term. This is one more rule. So there are 3 4 rules of like you have to take care while finding out the worst case time complexity or the time complexity, we can say. We are not taking here the exact case, right? We are just considering the worst case, bigger notation. So we ignore these things. These are bigger rules. When you're writing complexity in bigger notation, you ignore constants, you just ignore less dominating terms. These things happens. You can do that thing, right? Because when you take larger, the size is increased, then these terms doesn't really matter. These are not making any significant or any difference. So we can ignore these. If suppose same, if time complexity is, if you are having one more for loop, nested for loop, then that would be order of n cube. But that's really bad idea to have this such kind of code having complexity order of n cube. So if order of n cube plus maybe you are having some like n square plus 100 plus n by 2, something like this. So simply you can write down this order of n cube because these are less dominating terms. So you can just ignore these. Simply take the higher order. N cube is, cube is highest one. So take this one. Order of n cube. That's it. Right. So see here in this only, in this method only, we have added, we are just having some linear search, this for loop. Then a loop is running from 0 to 100. Then one more loop, nested for loop from 0 till n, from 0 till n. So it's n square times. So these statements would be executed n into n square times. Okay. So the total time complexity for this would be, at first it's n, then plus 100, then plus we are having n square as well, n square. So it's like n square, right? Now you can ignore this constant we know, and apart from this, the less dominating term is n, so just ignore this, and the complexity would be order of n square only. So this is how, like, you have a code. This is how you can calculate the time complexity of that method or any function. And always consider larger amount of data for finding complexity that we know. There are more rules like loops. The time complexity of a loop is the complexity of the loop body multiplied by the number of iterations. Okay, this thing we have told. If you have conditional statement, then also we can calculate function call. We will see this thing later about function call, recursive call and all. But recursive call basically we'll discuss later. But function call we have seen, like linear search was a method and we were calling that function once. So how to calculate the time complexity, we have seen that thing, right? The rules I have told you what are some rules. So these are some few examples how to calculate the same example, linear search, how to calculate this thing I have told you. This is for like nested loop, how to calculate. These are nested loops, so time complexity would be n square. The outer loop iterate n times and the inner loop iterate n times for each iteration of outer loop. I hope you understand this line. So the time complexity is n into n. Here it's n into m because the arrays are different. I mean, the input is different. Here it's array 1, it's array 2. So the length may be different. This array is of size n, having 50 elements. This array is of size m, maybe 10 elements or 100 elements or 1000 elements. If both are same, array 1, array 1, then it's n square. If different, then take different terms. Here like n and m. This thing also you need to take care. If loops are iterating on different input size data or different arrays, consider taking different terms for that. N, m. If array 1, then take n squared. It becomes like n square. Okay. So this is for nested loops. If one more loop is there, then n cube, that kind of thing. So now comes to, I hope you got the space time complexity, space complexity now. Space is like the memory requirement. So it measures the amount of memory an algorithm uses in relation to the input size. So space complexity basically, it's like a combination of the input size. Suppose we are having an array of size n. So obviously we take like in memory that for storing those n elements we take some space. Next is auxiliary space. That is like extra space or temporary space required during execution of that program. If required, that will also be added. So that fixed space plus auxiliary space, that is space complexity. Okay. Sometimes you need, like if you are having an array and you need to reverse this array. So we'll give an array to you, and while writing the program, in that execution time, you take a temporary array. Again, one more array you take, that is temporary array of same size. Suppose size is 5, so same size you take array 5. It's like array 2 you take. This is suppose array 1. To reverse this, and you just put this element here, this element here, something like this, and like this you reverse the array. So you have taken an extra array. And so you have taken one more n. So it's same like it would be order of n only. So this is taking n, the extra memory, extra array you have taken, that is of same size. So you can take n plus n. It's 2n. Ignore the constant. It's order of n. Something like this. So the space required. So generally, in interview, like you have to focus if they ask space complexity, then not the input size and all. The extra space your algorithm takes, if you are taking an extra array or not or something like this, that comes under space complexity. But actually, it's combination of both. The fixed space required plus the auxiliary space required, right? So it includes the memory used for the input data. Obviously, this, if suppose array of size 5, so this is input data. Auxiliary data structure, if you are taking some extra temporary array, that thing, and some variables. If you take variable, int x is equal to 0 and this thing, so that is constant. So it's order of 1. That doesn't matter really, right? If you're taking some 2, 3 variables, that would be order of 1. Or if you're taking again one more variable, again order of 1. So 1 plus 1 plus 2, 1, something like this. That is constant, so you can ignore these, right? So like this, if an algorithm that creates a copy of input array, like in this case, then space complexity is order of n only. It's 2n, or you can say order of n only. So space complexity is not that much tough, or it's not that much like more important. But it plays a crucial role when you have some limited resources. In that case, you need to take care about the space complexity of your approach you are using, right? So it's like you can say space required or consumed by the program in the main memory during the execution. That is space complexity. That's it, right? So I guess you got it. Space complexity and time complexity. Auxiliary space. Here we have which represents the extra space or the temporary space you use beyond the input itself during execution. That is auxiliary space. Some algorithms are in place. In place means they don't require any extra space during execution. So those are in place algorithms like bubble sort. That is in place algorithm. So they are having time complexity order of 1 only, right? Use simple statement. If you take like int x is equal to 0. So those variables take, obviously take some space, but that doesn't matter a lot. It's order of 1 only, constant time. Okay. So space complexity, like in this case, if this is the algorithm, so space complexity of this is apart from the input array. Generally, we don't take while calculating space complexity this thing. So space complexity of this algorithm or this method is, see, we are writing here in total is equal to 0. So this is taking order of 1. Then this variable int num, this is also simple variable. So order of 1. In obviously it is taking some space. So total plus sum order of 1. This is also order of 1. So total space complexity for this is order of 1 only. That's it. Because we don't need any extra array and all. We are not needing any auxiliary space here. Just the arrays has been passed. So we are not calculating any copied array of this array. So we are not needing any extra space. So that's why it's order of n only, regardless of the size of the input array. Size of the input array is maybe n, but that generally we don't take. Okay. So I guess that's it about space complexity and time complexity and bigger notation. I hope you got this, because this lecture is very important. Otherwise, you will not get, whenever we were discussing the more some algorithms and all. So every time we will see complexity of those, time complexity and space complexity. So better you have the idea of these things now. What is bigger notation and all. Now there are two more terms that are theta and omega. Let me just discuss these things in brief. So we have omega, theta, and big O. So it indicates the worst case big O notation. With omega, we denote the best case, and with this, we denote the average case. So these are asymptotic notations. But once we proceed in this course, then you will get idea of these terms better. But for now, we just understand this thing. To indicate worst case complexity, we need big O notation. That is important one. For best case, it's omega. To represent average case complexity, this is the lower bound, this is upper bound. And for average case, we denote this with theta, right? So we'll see about these notations later in detailed manner, right? So that's it about time complexity and space complexity. I hope you got this. In next video, we'll see some practical examples. I'll show you some code snippet, and we will calculate the time complexity and space complexity for those algorithms, for those approaches. So now I'll see the next lecture. Till then, bye bye. Take care.